My name is Robert Smith, and I'm with New River Community College's Academic Assistance, and today we are looking at quantum mechanics. Just a very simplified version of quantum mechanics, might I add. An electron of mass 9.1094 times 10 to the minus 31 kilograms is moving at a speed of 9.0 times 10 to the 6th meters per second. If the uncertainty of measuring its speed is 0.9% of the speed, calculate the uncertainty of the electron's position. Now, before I go any further, let me say that for Chemistry 111, the likelihood of there being a problem regarding this is relatively low. But if you're interested in chemistry, if you're interested in physical chemistry, quantum mechanics, this might be useful. So let's start by assigning what the uncertainty of the electron's speed is. So the uncertainty, I'm going to call it delta U for the electron's speed, is our percentage in decimal form, so 0.009, times the speed that was given, 0.0 times 10 to the 6th meters per second, which when you do the arithmetic out, you find that it is 8.1 times 10 to the 4th meters per second. So that's our uncertainty of speed. So knowing that momentum is equal to mass times velocity, we can also say that our delta, our change in momentum, is going to equal mass times our change in speed. And in this case, our change in speed is given as 8.1 times 10 to the 4th meters per second. So solving for delta P, we have 9.1094 times 10 to the minus 31 kilograms times 8.1 times 10 to the 4th meters per second, which gives us, for delta P, 7.378614 times 10 to the minus 26. And that's going to be in kilogram meter seconds. Meter per second. Okay? This will all become relevant very soon. So one thing that we know from quantum mechanics, the brief intro that we get, is that our change in position times our change in momentum has to be greater than or equal to Planck's constant over 4 pi. Doing a little bit of manipulation and generalization, we can find that our change in position has to equal the Planck's constant over 4 pi delta P. Planck's constant is equal to 6.63 times 10 to the minus 34 joule seconds. And in doing this, we're going to find that our delta X, change in position, is going to be 6.63 times 10 to the minus 34 joule seconds over 4 pi times that 7.378614 times 10 to the minus 26 kilogram meters per second. I carry over as many decimals as I feel is necessary, but we're going to end up truncating this at 2 significant figures because that's how much we're given for the speed up here. So when you do the arithmetic out, you'll find that delta x is 7.2 times 10 to the minus 10 meters, which gives us the uncertainty of the electron's position. So you cannot predict the electron's position with any certainty that is greater than 7.2 times 10 to the minus 10 meters. That may not seem significant except when you're trying to do particle physics or something similar thereof. But that's our brief foray into quantum mechanics. I don't expect that you'll encounter this much in your class, but it's always useful to have a little extra knowledge. And if you didn't understand this the first time, go ahead and watch it again, and hopefully it'll sink in. I know it's a little heavy in the content, but you can muddle through it if you care to. If not, I'm sure you'll find that this, if you're pursuing the sciences, specifically physical sciences, either chemistry or physics, this kind of thing will occur further on down the line when you're either doing physical chemistry or any kind of modern physics. I'm sure it shows up quite a bit.